Welcome back, everyone, to our ongoing deep dive into the OEIS. It's that incredible online encyclopedia of integer sequences.
It's quite a treasure trove for number theory enthusiasts.
Definitely. We're exploring the fascinating patterns and hidden depths these sequences reveal about the world of math.
And sometimes they pop up in unexpected places, too.
Absolutely. And for today's deep dive, we're focusing on A000123.
Ah, yes. The binary partition function.
That's the one. It's got some surprising connections to things you might not expect at first glance.
You've got binary numbers, of course, but then there's also coin change problems and even hints of computer science lurking in there.
All right, now you've got me intrigued. But before we get ahead of ourselves, let's break down the basics. What exactly are binary partitions?
Well, imagine you've got an even number, like, say, 10.
Okay, 10, got it.
A binary partition is basically a way to write that number as a sum using only powers of 2.
So like 8 plus 2.
Exactly. Or 4 plus 4 plus 2.
Or even 2 plus 2 plus 2 plus 2 plus 2.
Precisely. And here's the key difference from just the regular binary representation of a number. You can use the same power of 2 multiple times.
So we're not limited to just using each power of 2 once.
Not at all. And the sequence, A000123, the binary partition function, it counts how many different binary partitions you can make for each even number.
So for 10, like we were saying, there are actually 10 distinct binary partitions.
That's right.
10 ways to build 10 using only powers of 2. That's pretty neat. So what makes this sequence stand out in the world of number theory? What makes it so special?
One of the first things that caught mathematicians' attention is the recurrence relation that generates this sequence. It's surprisingly simple.
Oh, how so?
It goes like this. AN equals AN1 plus a floor N2.
On the surface, that does seem pretty straightforward. How would that work in practice, though?
Let's say we want to find the fifth term in the sequence, A4.
Okay.
We need the previous term, A3, and the term at floor 42, which is A2. Add those together, and boom, you've got a 4.
So each new term is built directly from the ones before it.
It's like a domino effect. But there's an interesting twist to this sequence.
Oh, what's that?
It has this odd-even pattern to it.
I'm listening.
So apart from the very first term, A0, which is 1, every single term in the sequence is even.
Wait, really? Every single term? But we're adding terms together? How does that even work?
That's the beauty of it. It was actually first observed by Churchhouse just by looking at the numbers, and then later on, Gupta came along and formally proved it.
Interesting. So even with this deceptively simple definition, there are already some surprising properties hiding beneath the surface.
Exactly. And it gets even more interesting when we start looking at the generating function for the sequence. It has a really elegant form.
Okay, I'm ready to dive into that. What does it look like?
It's an infinite product. It goes 1 over 1 minus x times 1 over 1 minus x squared times 1 over 1 minus x to the 4th times 1 over 1 minus x to the 8th, and so on. Each factor represents a power of 2.
I have a feeling there's a good reason we're using an infinite product here, especially since we can repeat the same power of 2 in our partitions.
You're spot on. Each of these factors makes sure we can use each power of 2 as many times as we need. For instance, that 1 over 1 minus x to the 4th factor, that accounts for all the ways we could include the number 4 in our partitions.
I see. So the generating function captures that unlimited use of powers of 2 that's at the heart of binary partitions. Does this connect to other parts of number theory at all?
It definitely does. If you're familiar with Euler's work on partitions in general, you'll notice a resemblance.
Euler. What would number theory be without him?
Right. This generating function for binary partitions is actually a special case of Euler's more general partition function. We just restrict ourselves to powers of 2, and we get this nice simplified form.
It's fascinating how limiting ourselves to powers of 2 leads to such elegant math. But I'm curious, how fast do these binary partition numbers actually grow?
That's a great question. And it turns out they grow faster than any polynomial, but slower than any exponential function.
So they're kind of in a sweet spot. Not too slow, not too fast.
Exactly. And figuring out exactly how they grow led to some significant mathematical work.
Ooh, like what?
Well, Mahler was one of the first to make some headway. Through his work, he managed to get an early version of the asymptotic formula for the binary partition function.
So it seems like different areas of math have contributed to our understanding of this sequence.
They really have. And then in 1948, N.G. de Bruijn came along and published a paper specifically on the growth rate of A000123. He refined that asymptotic description using some really powerful tools.
What kind of tools are we talking about here?
Things like Tauberian theorems and complex analysis. He used them to analyze that infinite product generating function and came up with a much more detailed description of how the sequence grows.
Wow. It's amazing how much depth there is to uncover in this seemingly simple sequence. What other discoveries did mathematicians make?
Well, around the 1960s, R.F. Churchhouse made some significant contributions. With the help of the Atlas computer, he was able to calculate a huge number of terms in the sequence, and this led him to make a now famous conjecture about the evenness of the terms.
So computers played a role in this discovery.
Absolutely.
Yeah.
Churchhouse observed that all the terms, except for the very first one, seemed to be even. And later on, Gupta formally proved it.
That's a great example of how computation and proof can work together to advance math.
It really is. But the discoveries didn't stop there. Even the recurrence relation for A000123 has a richer story behind it than you might think.
Oh, I'm all ears.
Donald Knuth, in his 1966 paper, An Almost Linear Recurrence, explored the recurrence relation for A000123 and connected it to the broader theory of linear recurrences.
So even the basic building blocks of this sequence have deeper ties to other areas of math.
Exactly, and the story of A000123 is far from over. Mathematicians like Euler, James Sellers, and even Neil Sloan, the founder of the OEIS, have continued exploring generalizations of binary partitions, and they've been finding all sorts of interesting connections.
It's incredible how this seemingly simple concept has led to such a rich and varied history.
It really is. And with any good deep dive, we're always left with more questions than answers.
That's the beauty of it, isn't it?
It is. I mean, if restricting ourselves to powers of 2 leads to such a treasure trove of mathematical insights, what happens if we use other building blocks? What if we use powers of 3 or other number bases? What other hidden gems are waiting to be discovered within the vast world of integer sequences?
Those are some fantastic questions to ponder. We've come a long way in this deep dive, from the basic definition of binary partitions to their surprising properties, their unexpected applications, and their rich, interconnected history.
It's a testament to the beauty and interconnectedness of math, where simple curiosity can lead to a lifetime of discovery.
Exactly. So until our next deep dive into the OEIS, keep exploring, and who knows what mathematical treasures you might unearth. So we've talked about how these binary partition numbers grow, faster than polynomials but slower than exponentials. Can you give us a sense of scale for these numbers?
Sure. Let's take a look at 100, the 100th term in the sequence. Turns out it's about 35,633, a 5-digit number.
Okay, that's getting pretty big already, considering we're only at the 100th term. What about the regular partition number for 100, just for comparison?
Oh, now that's a completely different beast. The unrestricted partition number, P100, it counts all the ways to break down 100 into positive integers with no restrictions whatsoever. That number is enormous, something like 190,569,292.
Whoa, that's a massive difference.
Yeah.
So even though AN grows pretty fast, restricting ourselves to powers of 2 really keeps things from blowing up exponentially.
It really does. And as you go to even larger values of n, that difference in growth rates becomes even more dramatic.
It's amazing how much of an impact that one restriction has. So where do these binary partition numbers actually show up in the real world? Are there any practical applications?
Absolutely. One of the most intuitive ones is the classic coin change problem.
Ah, I see where you're going with this.
Imagine you have coins and denominations that are all powers of 2. $1, $2, $4, $8, and so on.
I'm following.
The binary partition function, AN, tells us how many different ways we can make change for, say, $10 using only those power of 2 coins.
It's the same concept, just applied to a real-world scenario. So if I want to make change for $10 using only those coins.
The binary partition function, a 5, tells us how many ways to do it.
So it's like we're taking that rigid structure of binary representation and making it more flexible. We're allowing multiple different combinations to get to the same total.
That's a great way to think about it. Now, let's move beyond coin change and delve into another area where these binary partition numbers make a surprise appearance. Non-squashing partitions.
Non-squashing partitions.
Yeah.
That's a new one for me.
It's a bit of a mouthful, but the idea is pretty interesting. Basically, a non-squashing partition is a way to break down a number into parts, and when you list those parts in order, they have this special property. The sum of the first, say, 3 parts can never be bigger than the 4th part.
Okay, let me see if I've got this straight. So if we take the partition 1 plus 2 plus 4 plus 8 for the number 15, that would be a non-squashing partition, right?
Yeah.
Because 1 is less than 2, and 1 plus 2 is less than 4, and 1 plus 2 plus 4 is less than 8.
Perfect. You've got it. And what's really cool is that the number of these non-squashing partitions for an even number like 2n, or even an odd number 2n plus 1, is actually given by our old friend an, the binary partition function.
So this sequence, which we defined in terms of powers of 2, ends up counting something that seems completely different, these non-squashing partitions. It really highlights the unexpected connections in math.
It does, and it doesn't stop there. A000123 also has applications in a field you might not expect.
Algorithm analysis.
Algorithm analysis, really.
Yep. Specifically in understanding how efficient certain types of algorithms are.
I'm intrigued. How does that work?
Think of a recursive algorithm. The time it takes to run, what we call its time complexity, can sometimes be described by a recurrence relation that looks like this: Tn1 plus T floor n2.
Hold on. The recurrence relation seems familiar. Isn't that the same one that defines our binary partition function?
You got it. That's exactly the connection. When we analyze the runtime of those types of algorithms, we end up dealing with our binary partition numbers. Knowing how an grows helps us figure out how the algorithm's runtime scales with the input size.
It's fascinating how a sequence that comes from number theory can suddenly give us insights into the efficiency of algorithms. It's a perfect example of how seemingly different areas of math can be connected in unexpected ways.
It really is. Now, to add another layer to this story, let's take a step back in time and look at the history behind A00000123. It might surprise you to learn that the study of binary partitions goes all the way back to the 18th century.
Oh, and who might have been involved back then?
Well, none other than Leonhard Euler himself.
Of course. It had to be Euler. The man had his fingers in just about every pie in mathematics.
He certainly did. And as a pioneer in the theory of partitions, Euler likely derived that infinite product form for the generating function we talked about earlier.
So we've got Euler dipping his toes into binary partitions back in the 1700s. But I understand things went a bit quiet after that. When did mathematicians really start digging deep into this sequence?
Well, it wasn't until the mid-20th century that things really picked up again. It seems like a lot of the key insights came from mathematicians working in seemingly unrelated fields.
Like who?
Well, there was Kurt Mahler. He was working on functional equations, of all things. And through his research, he actually managed to come up with an early version of the asymptotic formula for binary partitions.
So he was able to get a rough idea of how fast these numbers grow.
That's right. But then, in 1948, N.G. de Bruijn really took things to the next level. He published a paper that specifically focused on the growth rate of A000123, and he brought some serious mathematical firepower to the problem.
What do you mean?
He used tools like Tauberian theorems and complex analysis to really dissect that infinite product generating function. This allowed him to refine the asymptotic formula and get a much more precise description of how the sequence grows.
It's amazing how much depth there is to this seemingly simple sequence. What other discoveries were made in the 20th century?
Well, in the 1960s, R.F. Churchhouse enters the picture. He had access to the Atlas computer at the time, which was a pretty powerful machine for its day.
So this is where computers start playing a role.
Exactly. Churchhouse used the Atlas computer to churn out a ton of terms in the binary partition sequence. And this led him to make a pretty important conjecture about the parity of the terms.
Parity? You mean whether they're even or odd?
Precisely. He noticed that all the terms in the sequence, except for the very first one, A00, seemed to be even.
Wow, that's pretty interesting. Did anyone ever prove his conjecture?
They did. Shortly after Churchhouse made his conjecture, Bruijn Gupta came along and provided a formal proof, not only for the evenness of the terms, but also for other divisibility properties of binary partitions.
It's a nice example of how computational exploration and rigorous mathematical proof can work together.
It really is. But the discoveries didn't end there. Even the recurrence relation itself, that simple little formula we talked about earlier, it turns out that has a deeper story to tell.
Oh. Tell me more.
Well, in 1966, Donald Knuth published a paper called An Almost Linear Recurrence. And in that paper, he dug deeper into the recurrence relation for A000123. He was able to show that even though it looks nonlinear at first glance, it's actually closely tied to the theory of linear recurrences.
So even the fundamental building blocks of this sequence have connections to broader mathematical concepts.
Exactly. And the exploration of 80000123 continues to this day. Mathematicians like Ole Redstead and James Sellers, along with Neil Sloan, the creator of the OEIS itself, have continued to investigate generalizations of binary partitions, delving deeper into those non-squashing partitions we talked about and discovering all sorts of interesting connections to other parts of math.
It's incredible to think that this seemingly simple idea of expressing an even number as sums of powers of 2 has spawned such a rich and fascinating area of research, spanning centuries and involving so many brilliant minds.
It really is a testament to the beauty and interconnectedness of mathematics, where a simple question can lead you down a rabbit hole of endless discovery. Who knows what other mathematical treasures are waiting to be unearthed in the vast world of integer sequences?
That's a great point. We've covered a lot of ground in this deep dive. We've explored the definition of binary partitions, uncovered some of their surprising properties, touched on their unexpected applications, and even journeyed through their rich history. But I have a feeling this is just the tip of the iceberg. There's so much more to explore in the world of integer sequences.
Absolutely. And that's what makes it so exciting. Every sequence is like a doorway to a new world of mathematical wonder.
Well said. So until our next deep dive into the OEIS, keep exploring, and who knows what amazing patterns and connections you'll find.